Fault friction can be categorized into static friction, present before an earthquake, and dynamic friction, which is present during earthquake rupture. Static friction can be described by WayLin's law, where sliding begins when the ratio of shear to normal stress reaches the value of friction. Static and dynamic friction are part of a more general description of friction, the rate and state friction. It is a formulation for friction observed from experimental data and provides relations between the coefficient of friction and velocity. A and B are constants for the instantaneous direct effect and time-dependent evolution effect respectively. They represent material properties. As experimental data has become more robust, variations of the rate and state friction has been proposed, but it remains a useful description for the evolution of friction. As friction changes, it affects the nature of ground shaking and extent of destruction. The fault zone consists of the damaged zone and the fault core. At shallow depths of up to 4 km in crystalline rocks, the fault core is primarily made of a fault gouge. Fault gouges are unconsolidated or loose angular material formed by grinding along fault surfaces. Tectonic movement along zones of brittle deformation forms fault breccia, which, if subjected to further frictional wear and grain crushing, forms fault gouges. Fault gouges are formed during cataclastic flow where grains are crushed. As it is difficult to obtain values for friction directly, lab experiments are carried out instead. Studies have shown that as fault gouges develop, friction increases. For steady state, the rate and state friction can be simplified. Back to the question of how friction changes for different slip rates. Let us look into constant slip rates. For each velocity or color, friction reaches the peak at the start of displacement. It then decreases exponentially before reaching a steady value. For higher slip rates, friction across the fault gouge gets smaller. Next, we can look at what happens when slip rate is not constant. When slip along the fault accelerates, irregularities on the fault surface melt due to heating, causing friction to decrease. Studies have revealed that the formation of fault gouges directly affects frictional changes as it accumulates to surfaces during slip. This is a possible model of friction for accelerating fault slip from rest with 5 stages. Stages 1 and 2 are the formation of fault gouges. There is limited change in friction due to the short slip distance. Next, as velocity increases to an intermediate level, friction decreases and the fault weakens. It is possible that the powder-like gouge material acts as a lubricant along the fault surface. As slip continues, the fault strengthens. The increase in friction could be due to increased heating, causing dehydration. At even higher velocities, slip becomes unstable, leading to failure and fractures. The fault gouge thus develops from a strong immature state to a weak mature state. What about the case where slip accelerates then decelerates? Friction increases during the initial strengthening stage. There is subsequent weakening as acceleration continues. Towards the end of the slip, friction heals rapidly on deceleration. The initial increase in friction could be described using the direct effect, while subsequent weakening and healing are described by the state evolution effect. Formation of AUTHIGENIC minerals can also affect fault friction. An example would be the breakdown of K-feldspar to illite. Minerals such as chlorite, illite, and smectite have been observed to have coefficients of friction much lower than that described by WayLin's law. Mineral transformations in clay gouges can thus produce clay-rich fault rocks with lower friction than silicate rocks, weakening the fault surface. Studies have also shown that as total clay content increases, friction decreases, thus weakening the gouge. This is likely due to the abundance of aligned clay materials in the matrix, which acts as a lubricant and minimizes